Swayam Prabha. Digital India. Educated India.
Welcome back to the video course on fluid mechanics. So, today we will start a new chapter, which is one of the most important in fluid mechanics, Navier-Stocks equations and applications. So, we have seen various aspects of fluid mechanics in the last few lectures, starting from statics, kinematics, dynamics of fluid flow, and then we discuss the dimension analysis. And now, in this chapter, we will more concentrate upon the viscous flows. So, as all of you know, viscous flow is very important, since most of the real fluid flows are, we have to consider viscous flows, and we have to consider the viscous effect in the derivation of the basic equations, and then we have to do the solutions, we have to get the solutions according to, by considering the viscous effects. So, as you can see here in this slide, so this is flow over an airfoil. So, we can see that, say when since if the fluid passing over the airfoil is viscous, then the flow pattern is totally different, what we considered earlier, like when we consider the ideal fluid flow or the potential flow. Then here, if the fluid flow is viscous, the effect is much more different. The way of approach is, we have to consider the viscous force, we have to consider the shear stress, all this we have to consider, and then we have to consider the applications accordingly. So, the objectives of this section or this chapter on Navier-Stocks equations and applications, first we will see the viscous flows, the importance of viscous flow, and then how generally we will be trying to solve the viscous flows. And then we will go to the Navier-Stocks equations, we will derive the Navier-Stocks equations, and we will discuss briefly the applications of these Navier-Stocks equations, and then we will discuss the exact solution for some of the simple cases, and also we will be discussing the plain Poiseuille flow, flow like Couté flow, Stokes flow, and porous media flow. So, the objectives of this chapter includes, say, the deliberations on the Navier-Stocks equations, its derivations and applications, and exact solutions available, and further studies on this. Okay, so now, as I mentioned, viscous flow, most of the real fluid flows are viscous, so that we have to consider the shear stress. So, the dynamics of fluid flow, which we considered earlier, we have derived the Euler equations and the Bernoulli's equations. There we neglected the effect of viscosity. So, the derivations of the equations are much simpler and solutions we can easily get. So, that is what we have seen as far as the Euler equations and the Bernoulli's equations are considered. And even though these equations are derived for the simple case of ideal fluid flow or potential flows, but still we try to use these equations with certain simplifications for the real cases. So, that is what we have seen in the earlier lectures when we discussed the Euler and Bernoulli's equations. So, but we can see that, so here either we are approximating that the viscosity is say negligible, so that the shear stress acting on the fluid is not much, and then we derived the equations, but that way it is an approximation and the accuracy of the solution will be affected by if you use a Euler equation or Bernoulli's equations. So, but when we deal with the real fluids, the viscosity is much more important and shear stresses play a major role. So, now when we consider this the viscous flows, so for most of the the real fluids which we deal in all the aspect of life is actually say real the viscosity effect is there, we have to consider the viscosity. So, the real fluid exhibits viscous effect, and then most of the cases this stick to the solid surface. So, when we put say in water or in a, say oil, when we put the spoon and then take it out, you can see that some fluid stick to the solid surface. So, there is stresses within the body. So, we have to consider this effect. So, here also you can see that the volcano, when the lava is flowing, you can see that it is highly viscous fluid is flowing, and then so we have to consider the viscosity effect, and then lot of parameters change. So, the Newtonian, when we consider the Newtonian fluids, we can consider most of the time the stresses vary linearly with respect to strain. So, we can derive the Newton's law of viscosity. So, Newton's law of viscosity is say very much used in all these derivations of the viscous flows. And then of course, we consider the say when a fluid is say when it is contained in a say in a container or in pipe or whatever it is, then say the fluid will be sticking to the solid surface. So, that we have to consider the no slip condition. So, you can see that if we consider here say the fluid is, say if you consider the pipe flow. So, as far as pipe flow is concerned, say the fluid is coming like this, then you can see that here the pipe is solid surface, and then so here the velocity should be 0 on this surface and this surface. So, you can see that the velocity variation is like this. So, this is the velocity. So, here say due to the no slip condition on the boundary. So, here a pipe flow is concerned this side and this side or throughout the periphery of the pipe, you can see that the velocity is 0 and the velocity will be maximum. So, viscous fluid is concerned, we have to consider this no slip condition as far as the with respect when it is contained in a container or in a pipe, as we have seen. So, viscous effect is very important, and then corresponding shear stress we have to consider. So, viscous flows, the shear stresses are taken into account, and then generally as we have seen in most of the other cases, we consider Newton's second law. So, that we can write the mass of the particle multiplied by the acceleration of particle, that will be equal to, we can equate the algebraic sum of the forces. So, here if you consider any particular case for viscous flow is concerned, the various forces will be net pressure force on particle, net gravity force on the particle, net stress forces on particle. So, if you consider the viscous flows and then using the Newton's second law with respect to a particle, we can write the mass of the particle multiplied by the acceleration of the particle, that will be equal to net pressure force on particle plus net gravity force on particle plus net stress force on particle. So, the stress force can be shear stress or normal stress or the pressure force depending upon the case. So, this generally for simple cases we consider like this, the Newton's second law for a particle, and then we try to derive the governing equation for that particular problem. So, it is difficult to derive for each individual case like this. So, we can derive a generalized equation. So, these generalized equations are called Cauchy's equation and the Navier-Stocks equations. So, before discussing the generalized equation for viscous flows, we will see a particular case how we are deriving the governing equation with respect to a simple case by considering the Newton's second law. So, let us consider the flow between two parallel plates. So, this earlier also we have discussed, but with respect to the viscous flows now what we have considered earlier in the laminar flow. Now, again here we are discussing when we deal with viscous flow how we can apply the Newton's second law and directly derive the relationship for velocity or various other parameters. So, here in this slide you can see that we consider the flow of viscous fluid between two very large parallel flat plates placed at a distance 2y apart. So, we can see here these two plates placed at 2y at a distance of 2y between them, and then the flow is taking place from left to right like this. So, this is the inlet of the flow, here is the outlet of the flow. So, we consider the axis at the center of the plate between the plates. So, here it is origin is here, x direction is here, y direction is here, and then acceleration due to gravity we consider. So, the elevation datum is here. So, as we have already seen in this case also, due to the no slip condition, the velocity variation will be like this, a parabolic variation. It will be maximum here at the center line and a minimum or 0 on the plates. So, here what we are trying to do, so here we consider the viscous flow. So, we derive the expression for velocity for this particular case for laminar flow. So, before deriving the equations, we will be using number of assumptions, so that we can use the Newton's second law. So, here the assumptions used are flow is steady and fluid is incompressible. So, there is the time dependent variables we can neglect since flow is steady, and density variation is not there since fluid is incompressible. Second assumption is fluid has viscosity, it will not slip at the surface of the plate, that means we consider the no slip condition. And as we have seen for this particular case, velocity distribution is parabolic. So, in this case the flow is two dimensional. So, we can use the continuity equation which we have derived earlier. So, in the differential form, the continuity equation is if u and v are the velocity components in x and y direction. For this case, we can write del u by del x plus del v by del y is equal to 0 as in equation number 1. So, due to the special nature of this particular problem, we can say that streamlines are straight and parallel to the x direction, as you can see in this figure. So, now here this particular problem is concerned, this velocity v is equal to 0. So, that del v by del x is equal to 0 and del v by del y is equal to 0. So, by using this condition here in the continuity equation, we can write del u by del x is equal to also 0. So, that means this is a parallel flow which we consider here with respect to this plate. So, flow between the parallel plates. So, v component is 0. So, we consider the velocity in the x direction u. So, now our aim is to derive the governing equation for velocity or other parameters for this particular problem. So, as we were using earlier, we can consider a small fluid mass and then we will consider what are the forces acting on that, and then we will be applying the Newton's second law. So, here since velocity does not change with x velocity field, so we got v is equal to 0. So, that means you can see here the velocity is varying with respect to y only. So, effectively this case is a one dimensional flow. So, now we will consider the flow with the velocity profile unchanging as the fluid moves downstream. So, this we can say this particular case the flow is fully developed flow, and then we consider a small fluid particle of size delta x by delta y like this, and then what are the various forces acting on this particle or this small volume of the fluid. So, here this particular case is concerned, we can see that the various forces acting here are mainly the pressure force. So, there is a pressure variation, that is why the flow is from left to right, and then since we consider viscous flow, so the shear stress we have to consider here. So, here if you consider the pressure flow on this face of this fluid mass, so here if P is the pressure, then this phase we can write P minus del P by del x into delta x by 2, and on this phase it is P plus del P by del x into delta x by 2, and on this phase it is P plus del P by del y into delta y by 2, and the corresponding other side it is P minus del P by del y into delta y by 2. So, these are the pressure forces acting on this fluid mass, and then the shear forces, or due to the shear stress the shear force we can write correspondingly, we can write on this phase it will be tau, the shear stress tau minus del tau by del x into delta x by 2, and correspondingly this side you can see it is tau plus del tau. So, this is on this phase actually, here tau minus del tau by delta x and delta x by 2 in this phase, and this phase it is tau plus del tau by del x in delta x by 2, and similar way on this phase the shear stress is tau minus del tau by del y into delta y by 2, and here tau plus del tau by del y into delta y by 2. So, for this particular case the forces acting are the pressure forces on the fluid mass or the fluid, the say delta y by delta x, the fluid, the mass of fluid which we consider, and then the shear forces or the corresponding the shear stresses on all the sides of the fluid mass which we consider. So, now say here our aim is to derive an expression for the velocity variation. So, here we are using the Newton's second law. So, in x direction if you consider, so here the mass into acceleration. So, delta mp, if that is the mass for this particular fluid element which we consider. So, delta mp into ax is the acceleration in the x direction. So, that is equal to delta fx pressure, the pressure component in x direction, plus delta fx gravity, the gravity force component, and delta fx the shear force component. So, from the figure, the earlier figure, so here we can see that the pressure component in x direction we can get as delta fx pressure is equal to minus del p by del x into delta x into delta y, and similarly the gravity force is concerned. So, here the shear force as well as the pressure force, and then of course, the gravity force also we have to consider for this problem. So, the gravity force is concerned, delta fx gravity we can write as rho into gx into delta x into delta y, where gx is the acceleration due to gravity in the x direction. And then the shear force is concerned, we can write this as in the x direction we can write as the difference between tau plus del tau by del y into delta y by 2 into delta x minus tau minus del tau y by del y into delta y by 2 into delta x. So, that we can write as del tau by delta y into delta x into delta y. So, this gives the shear force, and then the acceleration is concerned, this as far as the fluid element is concerned, acceleration ax is equal to del u by del t plus u into del u by del x plus v into del u by del y. So, here since we consider steady state flow, del u by del t is 0, and this del u by del x we have already seen for this parallel flow, it is 0, and then V component is 0. So, you can see that finally, the acceleration is equal to 0. So, now if you substitute in these equations, since the left hand side here mass into acceleration is already 0. So, you can see that this becomes 0, and then we can just equate the algebraic sum of the forces. So, now the pressure force we can write as del p by del x delta x into delta y, and gravity force rho into g x into delta x into delta y, plus the shear force del tau by del y into delta x by delta y. So, we can add all this, and then if you use the Newton's second law, we can write minus del p by del x plus rho g x plus del tau by del y is equal to 0. So, this is coming from the Newton's second law. So, now here we introduce, so we assume the z coordinate pointing opposite to the gravity vector, so that we can just approximate this rho g x in this fashion. So, here we can write equation number 2 as del p by del x minus rho g, this x direction with respect to z we can write as del z by del x. So, minus rho g del z by del x plus del tau by del y is equal to 0. So, this equation 2 is transformed this way, and then here for constants p and g. So, the pressure and acceleration due to gravity we can write equation number 2 as minus del by del x of p plus gamma z plus del tau by del y is equal to 0 as in equation number 3. So, in a very similar way, in y direction we can write as minus del by del y p plus gamma z plus del tau by del x is equal to 0. So, now here we get an expression with respect to the shear stress. So, we can use Newton's law of viscosity to convert to get in terms of velocity. So, here now the velocity profile is not changing in x direction as we have seen. So, hence del tau by del x is equal to 0, that means in y direction is concerned, this equation become del by del y of p plus gamma z is equal to 0. So, pressure distribution is from this equation number 4 we get the pressure distribution is hydrostatic. So, now as far as equation 3 is concerned, this we can write as, so now this pressure is varying only with respect to x. So, we can write minus d by dx of p plus gamma z, and then plus del tau by del y is equal to 0 as in equation number 5. So, here if we are assuming, so the flow is laminar, so that we can write the rate of shear deformation of particle, we can tau is approximately equal to the rate of shear deformation of fluid particle, that means the shear stress is approximately equal to rate of shear deformation. So, that this phi dash that is equal to half del u by del x plus del v by del x. So, here you can see that this become del u by del x is 0. So, that this become phi dash is equal to half del u by del y. So, that we can write tau is equal to mu du by dy, which is also coming from the Newton's law of viscosity. So, now directly we can write this from the Newton's law of viscosity and substitute here. So, that we will get, so in this equation if you substitute equation number 5, if you substitute from the Newton's law of viscosity, tau is equal to mu du by dy, finally we get minus d by dx plus of p plus gamma z plus mu del square u by del y square is equal to 0. So, now finally we get the velocity variation as a function of y. So, that we can write mu d square u by dy square is equal to d by dx of p plus gamma z. So, here in this particular case, if you write p tilde is equal to d by dx of p plus gamma z. So, that we can write d square u by dy square is equal to p tilde by mu as in equation number 7. So, we finally get an expression for velocity in terms of pressure. So, we can integrate times this expression d square u by dy square. So, that we will get the velocity u is equal to p tilde by 2 mu y square plus c 1 y plus c 2. So, integrate by twice we get this expression. So, now for this particular case we have the boundary condition. So, the flow is between two parallel plates. So, on the top as well as bottom where the fluid touches the plate, there we can assume the velocity is 0. So, that we will get the boundary condition, two boundary conditions. So, the boundary conditions here are, and y is equal to plus or minus y, u is equal to 0. So, we get C 1 is equal to 0, and finally, we get C 2 is equal to minus p tilde y square by 2 mu. So, finally, we get an expression u is equal to minus p tilde y square by 2 mu into 1 minus y by y whole square. So, here now with respect to this figure we can see. So, here we get a velocity variation is parabolic as now we have derived. So, we have applied the boundary conditions and used the Newton's law of viscosity to get an expression for this velocity variation. So, that is what we did here. So, this here in this particular case we considered the origin as on the central line of the between the plate. So, we get an expression for u as minus p tilde y square by 2 mu into 1 minus small y by y. So, this y gives the variation. So, whether on the between the plates. So, the y is starting from the central line between the plates. So, this is the expression for the velocity. So, now for this particular case we know that the velocity is maximum at the center. So, y is equal to 0, we can get the maximum velocity u max is equal to minus p tilde y square by 2 mu. So, this is the maximum velocity, and then if you want to find out the average velocity, v bar is equal to 1 by 2 y integral minus y to y within the limit u dy, that is equal to, if we integrate we can write minus 2 by 3 p tilde y square by 2 mu. So, that we can show that this will be the average velocity will be 2/3 of the maximum velocity. So, now in this expression we can put back with respect to the pressure variation. So, p tilde we can write as by with respect to d by dx of p plus gamma z. So, that is equal to u is equal to minus y square by 2 mu d of p plus gamma z by dx into 1 minus y by whole square. So, this is the final expression, and u max is it can be written as minus y square by 2 mu of d of p plus gamma z by dx, and v bar is 2/3 u max as we have already shown, that is equal to minus y square 3 mu d of p plus gamma z by dx. So, like this we can derive various parameters. So, here the aim of this deliberation here is, so for viscous flow we consider the viscous effect, that means the shear force and the pressure force and also the gravity force are considered, and for this simple case of flow between parallel plates which is one dimensional parallel flow, there we have derived the equation for velocity variation. So, by here we use the Newton's second law to derive the equation. So, very similar way for various simple cases as demonstrated earlier in the case of when we discussed the laminar flow problems, we can derive various expressions for simplified cases. So, now in a very similar way our aim here is to derive the fundamental equations for the viscous flow. So, here what we are going to discuss further is, say we are deriving the fundamental equation which are called Navier-Stocks equations, or the first form of the equation is Cauchy's equation, and then say later Navier and Stokes they very modified this equation and called as Navier-Stocks equation. So, our aim here is to derive the equations which are generally applicable to any kinds of problem. So, applicable to most of the fluid flow problems. So, first we will derive the Cauchy's equations. The Cauchy's equations are applicable for all kinds of problems, compressible, incompressible, or all varieties of fluid flow problems, and then we will discuss, especially when we consider the incompressible fluid flow, we will derive the from the Cauchy's equations, we will derive the Navier-Stocks equation. So, here as I mentioned, as we have already discussed for the flow between parallel plates, here we will use the Newton's second law and Newton's law of viscosity. By using the differential approach, we will derive the basic equations. So, first we will derive the Cauchy's equations, and then based upon the Cauchy's equation we will derive the Navier-Stocks equations. So, here the fluid flow problems which we generally consider 3-dimensional nature, but here for to derive the equations we are using 2-dimensional flow, so that it will be much easier to understand. So, the steps involved for 3-dimensional flow equations are also same, but here we explain as far as 2D flow, 2-dimensional flow is concerned, and then we will discuss the 3-dimensional equations, but the derivation is for 2-dimensional flow. So, now let us consider. So, here we derive the Cauchy's equation. So, let us consider an element within the fluid as shown here. So, here a fluid element of size delta x, delta y and delta z we are considering. So, here the various forces, as we have seen earlier, the forces are the pressure force. So, if we consider this fluid element, delta Fx pressure and delta Fx gravity, the gravity force, and delta Fx stress forces. So, stress can be normal stress or shear stresses. So, now either this phase or with respect to the x direction or y direction, we have to consider the pressure force, gravity force and the stress force. So, if we consider 2-dimensional flow with a constant velocity, so if we use Newton's second law of motion as we have discussed earlier. So, here for this flow problem we can write the Newton's second law, mass into acceleration is equal to the algebraic sum of the forces. So, here for this fluid element which we consider, the mass is delta m p, and then if acceleration is x direction is ax, then we can write delta m b into ax is equal to delta Fx pressure plus delta Fx gravity plus delta Fx stress. So, it is written in this equation number 1. So, in x direction delta m b into ax is equal to delta Fx pressure plus delta Fx gravity plus delta Fx stress. So, similar way in y direction we can write delta m b into ay, acceleration in y direction, that is equal to delta Fi pressure, delta Fi gravity plus delta Fx stress. So, now as far as the mass of the fluid is concerned, fluid element is concerned. So, if rho is the density and here we consider fluid element of size delta x and delta y and delta z size. So, mass is equal to delta m b is equal to rho into delta x into delta y into delta z, and then acceleration is concerned, the local acceleration and convective acceleration we consider. So, in 2-dimensional problem which we consider here, ax is equal to del u by del t plus u into del u by del x plus v into del u by del y, and ay is equal to del v by del t plus du into del v by del x plus v into del v by del y. And then the pressure force here for this typical problem, here we can write the pressure force. So, here it is explained further. So, here this fluid element is delta x by delta y. So, the pressure and stresses acting on the rectangular fluid particle are written here. So, here the pressure force in this direction P minus del P by del x into delta x by 2, and the other direction P plus del P by del x into delta x by 2, and here this direction the pressure force is P plus del P by del y into delta y by 2, and here this direction pressure force is P minus del P by del y into delta y by 2. And then if you consider the normal stress force, so here this phase it is sigma x minus del sigma x by del x into delta x by 2, and here this phase it is sigma x plus del sigma x into delta x by 2, and on this phase sigma y minus del sigma y by del x into del y by 2, and on this phase sigma y plus del sigma y by del x into del y by 2, and similar way these shear stress components. So, here this direction it is tau y x plus del tau y x by del y into delta y by 2, and on this phase tau y x minus del tau y x by del y into delta y by 2, and on this phase it is tau x y minus del tau x y by del y delta x by 2, and on this phase tau x y plus del tau x y by del y into delta x by 2. So, these are the pressure and stresses acting on the rectangular fluid element. So, now if you consider the net pressure force, we can write here del f x pressure is equal to del p by minus del p by del x into delta x into delta y into delta z, if we consider the fluid element thickness as delta z, and delta f y in the y direction pressure force is concerned minus del p by del y into delta x into del y del z, and similarly the gravity force on the fluid element del f x gravity is rho g x delta x delta y delta z, and del f y gravity is rho g y delta x delta y delta z. So, here now the forces, the stresses are the normal stresses and the shear stresses. So, depending upon the cases for the flow which we consider, definitely shear stresses are there, normal stress whether depending upon the problem we consider. So, now all the stresses are shown here. So, by considering the force on the particle other than the pressure, so del f x stress with respect to the normal stress and shear stress we can write as, with respect to the fluid element here we can write del sigma x by del x plus del tau y x del y by del y into delta x delta y delta z. So, that is the net stress force in the x direction, and similarly the net stress force in y direction can be written as del sigma y by del y plus del tau x y by del x into delta x delta y delta z. So, now all the force components, the stress forces including the normal stresses and the shear stresses and the pressure forces and the gravity forces are known, and we have already seen the mass of the fluid element and the acceleration. So, now we can use Newton's second law to substitute all these components to get the final form of the equation. So, now substituting the mass and acceleration and all of the forces into equation 1 and 2, that means in 2 dimensions equation we are writing the equation for 2 dimensional cases. So, equation 1 and 2, and then shrinking our particle to the point x y, here this figure shows we consider this equation 1 and 2 and then we consider a particular point in the differential approach. So, we can get rho into del u by del t plus u into del u by del x plus v into del u by del y is equal to minus del p by del x plus rho g x plus del sigma x by del x plus del tau y x by del y, equation number 3. So, this is the final form of the equation, and then in y direction we get rho into del v by del t plus u into del v by del x plus v into del v by del y is equal to minus del p by del y plus rho g y plus del sigma y by del y plus del tau x by del x, equation number 4. So, this equation number 3 and 4 are the basic equation as far as viscous flows are concerned, and these equations are called Cauchy's equations. So, these equations are in 2 dimensions. So, we got 2 equations from the Newton's second law of motion. So, we got 2 equations. So, with these 2 equations in 2 dimensional case, we can supplement with respect to the continuity equation. The continuity equation gives del u by del x plus del v by del y is equal to 0. So, here for 2 dimensional problem, if you inspect, if you check this equation 3, 4 and the continuity equation, we have for 2D problem we have 3 equations, but you can see we have 7 unknowns. The unknowns here, unknowns can be u v the velocity component, p the pressure component, sigma x and sigma y the normal stress component, and tau x y and tau y x the shear stress component. So, this is the case for 2 dimensional problem. So, for 3 dimensional problem in a very similar way, we can write the equations. So, there will be 3 equations, the Cauchy's equation, 3 equations will be there, and then we can supplement with respect to the continuity equation for 3 dimensional flow. So, here the unknowns. So, if you consider these 3 equations of motion derived using the Newton's second law and the continuity equation, we will be having 4 equations, and then we can see that there will be 10 unknowns, u v w the components and the pressure p, and 3 stress components sigma x, sigma y, sigma z, and 3 shear stress component. So, 3 plus 3 plus 3 velocity. So, 9 plus 1 10 unknowns for general cases, and here we have got 4 equations. So, depending upon the problem, we can supplement with various other equations like equations of state, and then we can try to solve the problem. So, this Cauchy's equation which we derived here are the basic equations for viscous flows. So, here this Cauchy's equations represent a unit balance of body and surface forces with inertial forces. So, here the Cauchy's equation which we derived here are valid for compressible and incompressible fluid flow. So, the advantage is say depending upon, so most of the cases which we discuss in this fluid mechanics course will be incompressible fluid flow, but the Cauchy's equation we can also use for compressible fluid flow also by considering the changing density also. And then here say this using the Cauchy's equation only we will be deriving the Navier-Stocks equation. So, the vector differential form we can write this the Cauchy's equation which we derived here in a vector form or vector differential form. If we consider P as this capital P as a stress component, then we can write G minus A into rho plus del dot P is equal to 0, where P is the stress forces, where G is the acceleration, A is the body force component, the acceleration of the. So, G is the acceleration due to gravity, and this is P is the stress, and this comes from the various other components. So, the vector differential form of the Cauchy's equation can be written like this. So, as I mentioned here, this equation, the Cauchy's equations are applicable to all fluid flow problems, either compressible, incompressible, or it is any kinds of. So, only thing is that depending upon the problem, we have to change certain say parameters, and then we can derive the equations. So, here now for the incompressible fluid flow problem, we are going to use the Cauchy's equations, and then we will be deriving the Navier-Stocks equations. So, now introduction to Navier-Stocks equations. So, Navier-Stocks equations, as I mentioned, if you for the incompressible viscous flows or even the viscous flows, these are the basic differential equations. So, we have already seen the form for Cauchy's equation, and based upon the Cauchy's equation, this Navier-Stocks equations derived in 1827 by Navier on the basis of intermolecular forces, and 1845 in the 19th century by Stokes by considering the normal and the tangential stresses as linear functions of the rate of deformations. So, as discussed, so these are the differential form of the consideration of linear momentum applicable in describing the motion of a fluid particle in any space and time. So, here the time component is considered, viscous time is considered, and then for the variation of any parameters, either velocity in x y z direction u v w or the pressure, we can utilize this equation. So, that is the beauty of the Navier-Stocks equation. So, here we derive the Navier-Stocks equation from the Cauchy's equation. So, now we have already seen there are 4 2D problems. So, as we have discussed here, 7 unknowns in terms of UVP, sigma x, sigma y, tau x y and tau y x, and 3D problems 10 unknowns. So, what we do here for Navier-Stocks equation, we try to represent these stresses, either normal stress or shear stress, in terms of say the velocity components by utilizing the Newton's law of viscosity or the stresses and strain relationship. So, here we try to relate the stresses to velocity field using the Newton's law of viscosity, and viscous stresses are proportional to rates of strain of fluid. So, in Cauchy's equation, the shear stresses are proportional to shear rate of strain. So, that we can write tau x y is equal to tau y x is equal to mu del u by del y plus del v by del x. And also, if we consider the normal stresses, normal viscous stresses, we can write, or we can assume in this particular case, normal viscous stresses are proportional to the stretching or volumetric strain rate. So, that we can write the normal stress component in x direction sigma x is equal to 2 mu del u by del x as in equation number 7, and sigma y is equal to 2 mu del v by del y as in equation number 8. So, let us assume for the case we consider the incompressible fluid flow, we assume the viscosity as constant. So, for this case, so this term del sigma x by del x plus del tau y x by del y, we can write by using this equation 6, this equation 7 and 8, we can write this is equal to mu into del square u by del x square plus del square u by del y square plus mu del by del x of del u by del x plus del v by del y. So, by using equation 6, 7, 8, these terms, the del sigma x by del x plus del tau y x by del y can be written in this form. Here the order of differentiation is interchanged for this last term. So, that is why this form is obtained. So, with respect to x and y, the order of differentiation is interchanged, and then this term is concerned. Here you can see that in for 2 dimensional problems, this del v by del x plus del v by del y for incompressible viscous flow, this term will be equal to 0. So, that finally we get this del sigma x by del x plus del tau y x by del y is equal to mu into del square u by del x square plus del square u by del y square. So, by using continuity equation, this term becomes 0, and finally, now we can use these approximations in the Cauchy's equation given here, rho del u by del t plus u into del u by del x plus v del u by del y is equal to minus del p by del x plus rho g x plus del sigma x by del x plus del tau y x by del y. So, here for these terms we substitute from the earlier this approximation. So, finally, we get rho del u by del t plus u into del u by del x plus v into del u by del y is equal to minus del p by del x plus rho g x plus mu into del square u by del y square plus del square u by del y square, equation number 9. So, this is the basic equation, Navier-Stocks equation for 2 dimensional problems in x direction. So, similar way for equation 4 in the y direction, we can write rho into del v by del t plus u into del v by del x plus v into del v by del y is equal to minus del p by del y plus rho g y plus mu del square v by del x square plus del square v by del y square as in equation number 10. So, for 2 dimensional problems, this equation 9 and 10 which we derived based upon the Newton's second law. These equations are called the Navier-Stocks equations for incompressible viscous flow. So, here we have demonstrated the case for 2 dimensions. So, in a very similar way we can derive for 3 dimensional problem, and here I have just written for 3 dimensional problem the equations are rho into del u by del t plus u into del u by del x plus v into del u by del y plus w into del u by del z is equal to minus del p by del x plus rho g x plus mu into del square u by del x square plus del square u by del y square plus del square u by del z square. This is the equation in x direction for 3D problem, 3 dimensional problem by considering the velocity components u, v and w. So, very similar way in y direction we can write rho into del v by del t plus u into del v by del x plus v into del v by del y plus w into del v by del z is equal to minus del p by del y plus rho g y plus mu into del square v by del x square plus del square v by del y square plus del square v by del z square, equation number 12. So, similar way z direction rho into del w by del t plus u into del w by del x plus v into del w by del y plus w into del w by del z is equal to minus del p by del z plus rho g z plus mu into del square w by del x square plus del square w by del y square plus del square w by del z square. So, 3 equation in x y z direction, and then we can use the continuity equation 3D del u by del x plus del v by del y plus del w by del z is equal to 0. So, here we have got 4 equations, and then we have got the unknowns as u, v, w, the velocity component and the pressure component if the density and the viscosity are known for the problem. So, these are the Navier-Stokes equation in 3D and 2D also we have seen. So, these are the fundamental equations for incompressible viscous fluid flow.